Morning, y'all. Gotta turn off Mick Jagger. Can't have Mick Jagger on. Sweet. Happy fog day. Thinking of it as fog. It's fall, and that's fog. Let's see. All right, have yourself. Let's just do a little big picture work here. Have yourself a look at that graph over there and see if you can interpret what it is saying. Is this a good graph? So I just want to give you kind of a quick big picture look at what calculus is really about. Let's see, let me check my internet. It says it's unstable. Why is it unstable? It looks pretty stable to me. I've kind of mentioned the concept of we're always looking at these parabolas and so forth, but I want to give you one just kind of big picture look at what calculus really is and kind of how it might really work. In the sense that it is, real world is not always nice parabolas and, these simple equations that we come up with, even these weird things that we make up. Like yesterday, we were doing multiplication and division. So if I come up with something like x cubed over the square root of x, I mean, that's fine to play with, but where would an equation like that actually come from? Well, once you look at this, you would probably agree there's a relationship, and this is what algebra is for. This is a real big picture flyover of what math is. You'd probably agree there's a relationship between the height and the volume of a tree. If a tree is taller, well, of course it's bigger, and then it's going to have more wood. And of course, this is the kind of thing a forester would think about. So again, this is a financial even application, or maybe it's a forestry application. And so you collect some data. So here's some data. And by the way, this is out of our Math 96 class, which is entirely dealing with what I would call real algebra. So a tree is, and notice that from science, the independent and dependent variable. Would you agree the height is kind of the independent variable? In other words, you sort of walk up to a tree and it's like, hey, look how tall it is. Well, as a result of that height, then it also has a volume. And of course, you would expect if the tree gets taller, then it has more volume. And by the time it's up to 75 feet, now it's got 1,235 cubic feet. And notice the units of that, because that's a little, I don't know, maybe confusing in the sense that the height would be measured maybe in feet. And then the volume would be cubic feet. I could have made that worse, by the way, because foresters measure it in board feet. I don't know if you know what that is, but we won't go down that road. Now, I used Excel to graph these points quickly, and notice it really is clear. Something that wasn't clear before, if you will, is what the relationship is. But notice that looks, well, I don't know, about linear. It's hard to tell, but it looks like it's going up in the shape of a line. And you probably don't know how to do regression on Excel, but what you're really trying to do is establish a relationship mostly in life so that you can predict the future. In other words, let's say you are a forester and you say, great, let's harvest that tree when it's, say, 1,400 cubic feet. Like that'll be big enough to do whatever we want to do. And so, you're wondering what year will that happen in? And so you're trying to establish a relationship. Well, let's do this using kind of modern technology. If I right click on this and say add a trend line to it, notice it is linear-ish, like that's straight-ish, but it also kind of, now I can tell that it's actually even kind of got a curve to it. And notice of my options over here for a trend line, like this is the kind of stuff that should speak to you because you've studied all this algebra. Like you should say, oh yeah, exponential equations. And you should even know what they're shaped like. But notice I kind of like the fact that Excel shows a little pre-graph over there, like it's kind of an upward curve and there's a straight line and the logarithm is a downward curve. Well, notice ours is an upward curve. So if I said, let's try logarithmic, that clearly isn't going to work. I mean, I don't know about you, but maybe you don't remember immediately what shape a logarithmic curve is. But I can see here it's downward. And so that's terrible. Like that's not a good model. And that's all. And that's an uglier equation on top of it. So that's not cool. And maybe exponential is good. Well, that's not so good. Exponential growth is really rapid growth, steep. And so that didn't fit it too good either. So a line's pretty good. I wonder about a polynomial. Hey, that's pretty good. And notice I have a choice over here. That's kind of cool. Cubed, squared. So that's a parabola right there. Notice that's a pretty good fit. So, hey, parabola, awesome. You know what those are. And then power. Hey, that's a pretty good fit too. I'm going to pick power only because it's probably something you're less familiar with. And it also speaks a little more closely to what we're studying right now. However, those last two were pretty good choices for a model. And so it's like, yeah, this thing really is curving. And notice the important thing about this to me is notice it's not perfect. You see how it doesn't quite hit right up there, but that's the way real math is. It's not always perfect. The equation doesn't always match the tree perfectly. In a sense, that could have been a bad year, could have been a fire year. And so it didn't grow as much then, or maybe it was a drought. And so, you know, trees are not going to perform according to some perfect curve, but they are going to perform in a sense according to math. And so just so you know what it is, I'm going to display this equation on the chart, and I'm even going to display the R value of that. And let's see on the chart, right there is good. And let's see, can I make it monstrous? If you've had a stat class, if you've that should speak to you, and or I should even say if your Math 111 teacher did their job, that should speak to you. In the sense that the R value tells you how good of a fit it is. And roughly speaking, that's like 99.98% accurate. Like that's a good fit. So this is a good model. Like we kind of own, you might say, we kind of own the relationship between tree height and tree volume. And so if we own this, does it make sense? We now have an equation that would predict the future. And so we aren't going to do this because this is an algebra question, but notice I said, you know, that X is the independent variable height. And we were interested in, you know, when the volume was 1400. So you should be able to say, hey, I'm interested in, you know, when the volume is 1400. And so you should be able to say, oh, that means plug 1400 in for Y, because 1400 cubic feet was the kind of the number in question. And so then you should be able to solve that equation. Like that's just algebra. But again, I bet that would challenge some of you just because you're not used to seeing real problems. Or you could just look at the graph. Like look at the graph. Doesn't it, if you just continue the graph in your mind's eye, doesn't it look like it's hitting, I don't know, at least reasonably close to this corner, which kind of puts it around 80 feet tall. Maybe you'd say it hits a little higher or lower, but you know, you don't have to do math to get a reasonable answer to this, which is kind of cool. And to the point of how people usually use math, let's see. I'll do that some other time. So that's what algebra is. Now what I'm curious about is what does calculus do here? So I'm going to make a copy of this and put it into our notes, but I want you to think about that. Like what would calculus add to this conversation? Why would somebody bring calculus into this? And again, I'm talking really like this is a forester trying to map how trees work for maybe even financial reasons. All of a sudden I'm thinking, how do I get a picture of this into my notes? Maybe I can't. I don't know if I can get this into my notes. Well, that's okay. So you might write down that equation, the equation that it gave, and even write down kind of what X and Y stand for. Because I can't copy this in because I didn't do this on my iPad, so I can't just take a picture of it. Well, I guess I could take a picture like old school style like this. I'll try that. later. And I would like to hear from some of you as to what you think the answer to this is. What does calculus have to do with this? Oh yeah, that's going to work just fine. We'll be all right. All right, goodbye. No. Yes. Now import from the photo library that picture. Let's crop it down a little bit just so we dial down all the other noise. And so that we can make it as big as possible. That's reasonably visible. So in a sense, what I'm trying to answer here is a big picture question, which, in a sense, this would have been a good way to even introduce this class. Like what is calculus anyway? So everything we just did is algebra. So what do some of you think? What does this add? Yay, I just, I did some calculus. What does this add to our discussion about this relationship between the tree's height and volume? What does calculus allow us to do?
Maybe it allows you to find a derivative to get the estimated year of when it can be harvested.
Yes, in the sense that, well, what does a derivative tell you?
It'll tell you the tangent line, or help you get the point where your tangent line's going, where you can develop your tangent.
Yeah, so a derivative tells us a tangent line. And keep in mind that a derivative is a slope. So if I just went down here and went rise and run, I don't want to count that. But what I want to know is, what does that mean? What are the units? If I rise, what are the units over here?
The rise over run.
No, I mean the units based on this tree.
Oh.
So it is, overall, it's rise over run. But if I'm rising here, notice that's in the vicinity of rising from 200 to 400. I mean, yeah. I didn't do that on purpose, but like, what does that mean when I rise? What are the units over there?
Cube feet. Y value.
Yeah, that Y value, which in this case is cubic feet. So you're actually cubic feet over, what's the run? What's its unit?
Just regular feet.
Yeah, it's regular feet. So that's kind of weird that they're the same unit. But keep in mind, this is like volume and this is height measured in feet. So that's what calculus does, is a slope, right? So what we're talking about here with slope in the real world is not slope, it's rate of change. In other words, our unit for this, our unit for slope, or in this case, not so much slope, but rate of change. That's a better way to look at it. This is why you do calculus, because of rate of change. Our unit would be cubic feet of volume per feet of height. Let's think about that for a second. And notice, I'll throw like I'll just aim at that Y and say V for volume and X is H for height, just so I remember that. And if I was going to rewrite this equation in the real world, I'd probably get rid of the X's and Y's and use V's and H's. But in terms of sticking things on graphs, calculators and so forth, X's and Y's are sort of all you get, but you just have to reinterpret that yourself. So what I'd like you to do is figure out quickly, since you know your stuff here. And let's just rewrite this equation, round it off a little bit. I mean, we're only talking about trees. Do we really need the equation to be that accurate? So I'm going to say 2.14. That's close enough, right? And then it's X to the 1.476. I think I'll just call it 1.48. So do you have the skill to figure out y prime now? Can you take a derivative of an equation like that? The answer should be yes. What do you get?
Got 3.1672x to the 0.48.
You said 167, so I'll just call it 17. So yeah, notice this was called a power equation, and therefore it's a power rule problem. So I can take 1.48 times 2.14. I didn't do it yet because you beat me to it, Justin, but it sounds like 1.48 times 2.14 would be about 3.17. So I don't think you screwed that up. And then you go 1.48 minus 1, right? Isn't that the power rule? Now, what does this new equation give us the power to do in this context? Again, it's slope, but the point is the slope is meaningful. What does slope mean here? Well, it's rate of change. So let's do that like at year 20. What's y prime at year 20? And let's do it again at 60. So now that you have a slope equation, you say, oh, y prime of 20, that just means put 20 in. So again, we're just rounding it off. So I'm saying 3.17 times 20 raised. By the way, raising something to the 0.48 power, what is that kind of like?
Kind of like cutting it in half.
Well, think about what
Right.
that exponent is. It's not
Square
cutting it
root.
in half. Who said that? Yeah. It's like square root. Isn't it like 0.5? This is pretty close to like 3.17 times the square root of x. It's pretty close to that, by the way. That's not what you're typing in. But let's see, I throw a 20 in and I got like 13.35. I'll just round it off and say like 13.4. And then I go back and throw 60 in there. It's very exciting. And I get 22.6. So my point is, this is not just slope. Yes, it is the slope of the tangent line, as Adrian correctly pointed out. It's the slope down there. And of course, looking at the graph, wouldn't you expect the slope down here at 20 to be flatter than it is up here at 60? So in a sense, you're not surprised that one of them was 13.4, one of them was 22.6. Now, who can answer this question? I don't know about you, but when I'm looking at that, that looks more like a slope of a half. What the heck is it doing being 13? Huh? That doesn't look like a slope of 13.
Is it because the scales of the graphs don't match up?
Nice job. Look at the scale of the graph. Along the x-axis, the heights are pretty small numbers like 10 and 20 and 30. But the heights, but the volumes are huge numbers, like they get up to 1400. And so the scale had to get modified. And so the visible view of the slope is all screwed up because the boxes aren't worth 1 each direction. Does that make sense? So if you had changed the scale so they matched, then it would be super steep. But that's just something that might occur to you. Now, most importantly, all of this, wonderful, good for you, but this is like utterly worthless. Everything we've done, unless you understand what that 13.4 means, unless you understand what that 22.6 means. It's not just the slope. It's not rise over run. That's too boring and it's totally irrelevant. Like, what does this mean? Somebody take a stab at it.
Is it the volume of the tree?
You're going in the right direction.
The volume of the tree and the height together make that number, correct?
Yeah, you're going the right direction. Like, isn't this the unit of slope up here? And there's no such thing as a number that's not a fraction. These are both over the top of 1, right? And notice they're both positive. So what does that really mean? This means that for an increase of 1 foot in height, which is in the denominator, that gives you an increase of 13.4 cubic feet of volume. Does that make sense? In other words, 1 foot of growth back there early when it was a kid and it was only 20. 1 foot of height gave it 13 more cubic feet of volume. But notice that rate is not constant. This was not a line. And so we get a totally different slope later on. Out there later, does it make sense 1 foot out here is worth 23 feet of growth? So a taller tree, 1 more foot of growth actually gives you more wood. Does that make sense? Like, slope is rate of change. Like, this is why people invented this stuff. They didn't just say, wouldn't it be fun to find the slope of a parabola? They invented it because of questions of this nature. Like, this is what calculus really is. There's no equation. Nobody gives you some equation. It's just, hey, go figure out what's going on with those trees out there, forester. You're a forester, paying you $80,000 a year. Like, go figure it out. And so for you to be able to say, you know, I own the relationship between height and volume, and I can predict things now, and I can tell you that, you know, when it's 80, it'll be about 1,400 cubic feet. That's really cool. Notice you had to be the one to create the equation in the first place using regression, which your calculator will do, which Desmos will do, which Excel will do. Excel is the best one because it's printable. Does that make sense? Like, you can actually make a printable graph. That graph I made is the kind of thing you see in a magazine. You know, it's nice looking. But then, you know, calculus adds one more consideration. Like, you can say, hey, you know, if we just waited 1 more year, you know, then it'll get 22 feet taller. And by the way, again, we can kind of predict the future. Like, we can, now that we own the relationship, we can go way out here to say when this thing is 200 feet tall, we can throw 200 in there and see what the growth rate is going to be out there. Can you tell this graph is getting steeper? To insert 0, I got 40. So that's not 40 feet. That's not 40 cubic feet. That's 40 cubic feet per foot. That's a growth rate. It's the rate of growth of volume relative to the rate of growth of height. And these units are a little weird. And I purposely picked this one because it's, you know, like cubic feet and feet. And so, you know, like, you could easily get lost in this. But this is what slope really is. Do you understand that? Rate of change. Like, this is the big picture of what calculus is about. And I bring this up just because I don't think people really understand what calculus is and what it can do. And also because this, you know, the best equation here was a power equation, and you know how to take that derivative thanks to the shortcut. Again, wouldn't that be fun to throw in x plus h in that and try to solve it kind of that way? That we have a shortcut called the power rule that handles power equations. And so this just adds one more element. You can say out there when this thing is 200 feet tall, now we're gaining 40 cubic feet. Every foot that thing gets taller, we're actually gaining 40 cubic feet of volume to the tree. And so, you know, it's more than double. It's triple what it was doing back when it was 20 feet tall.
Mr. Gardner?
Yep.
Correct me if I'm wrong, but isn't this graph inaccurate to a certain extent? Like, it's good for predicting now, but once it reaches a certain height, because this line goes on forever, trees can't grow forever.
Yeah. Everybody understand Faith's point? Like, does this just go on forever? The tree is 5,000 years old. No, it dies at some point. And in a sense, where mathematicians call that extrapolation. What we did before is interpolation, which is we're looking inside the data that we have. And so we can be really sure. But beyond that, the further away you go from your actual data, the more you don't know. Like, what if global warming goes away or shows up or actually is real? I don't think it's real. What if something changes? And so can you really be that confident, you know, going out there 100 years later? You're exactly right, Faith. The answer is, well, not really. I mean, that'd be your best guess still. You know, you have no evidence to the contrary. You say, hey, and you just would qualify it by saying if this pattern continues, and of course, this would be relative to how trees work. Like, they don't get 5,000 years old, but they do get 200 years old. And so it wouldn't be weird to make this guess, but you could definitely be wrong. So that's an excellent point. We'd be better off predicting like 80 and 90 because that's not that far away from the data. Go way out there at 200, much more risky. Do you have questions about that? Again, this is just extraneous to what we're doing. We're standing back from the daily grind and saying, what the heck are we doing here? In my opinion, like when you go job hunting someday, like if you could do that, like you're a veterinarian, for instance, and it's like, who needs calculus? Well, true in one sense, but if you could actually take data on a dog and how they're changing based on some treatment that you give that dog or that horse or something of that nature, you could take data, you could find an equation that modeled it and make predictions. Like if you could do that and you were applying for a job, I'd be like, wow, this person can take care of business. I'm going to give you the job. You know, could you throw something like this in an interview? Or could you just be a good vet and do this and, you know, be able to track things a little bit more? Can you speak the language of algebra and then even make use of calculus? And by the way, in this particular problem, I'd say, I don't know, as calculus is making a huge contribution to this. I think the algebra part was actually the most important because you can just kind of predict how big it's going to be down the road. Calculus is just kind of a little, you know, icing on the cake sort of a thing. But that's what growth rate really is. That's what slope really means when it's not just a boring graph, when the units actually have a meaning. How's your brain? Is it hurting or is it bigger? By the way, I graduated from college with a math degree and couldn't have done any of this stuff. Like I just sat there doing the assignments the teacher gave me, just like you. So if you look at this and think, man, I should have been paying more attention. Like we don't do a very good job teaching like what math really is. And I would say I didn't understand what math really was until I, you know, taught for a long time and began asking my own questions. But I wish somebody had showed me stuff like this, I guess is what I'm saying. Let me show you something else that's kind of cool that pertains to what we just learned. And I just want to spend a few more minutes looking at quotient and product rules. Let's look at the Witch of Agnesi. What in the world is the Witch of Agnesi? Maybe I'll post this to the notes later if you're a person who's interested. But again, these are just things I run across over in my life in different places. And I'm like, oh, that's pretty interesting. That's pretty cool. I think I'll show that to somebody. And so I won't go through this, but I just sort of made a quick Word document about all the things I found about this that I thought were interesting. And so the Witch of Agnesi, well, I don't have this memorized. I'm looking at this with you, but what's her first name? Maria Agnesi, born in 1718. She was the daughter of an Italian math professor, child prodigy, blah, 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 awesome gal, so forth. She comes up with this curve over here. And you might think witch, like what did she do? Boil cats or something? There's a bit of an explanation as to how that came about, but this particular curve right here, which was named by her, notice its equation, y equals a cubed over a squared plus x squared. What does the a represent? Stare at that a minute.
Is it a function of x?
Not even a function of x. Notice what it is in the picture. See this right over here?
Oh.
So it's kind of like this curve that ramps up from the ground and then sort of peaks over the top of a circle, kind of lands, spends a little time, well, I guess you might say tangent to the circle, and then it kind of goes back down to the ground again. And notice the A is actually just a number. Remember, the lower letters in the alphabet are just constants you haven't chosen yet. So A is like 2 or 6 or 8. You got to put a number in for that, whereas the X stays a variable. So if you stuck in A is 10, apparently from this picture, then the diameter of this circle right here would be 10. And so this curve would kind of make it up to a height of 10 and then drop down again if we're to graph this. And you might graph this on your graphing calculator while I'm rambling here. I'm going to do it in Desmos in just a minute too. But notice the Witch of Agnesi is used in spectroscopy from physics for fitting the shape of spectral lines in situations where the bell curve is not quite right. I don't know about you, but I'm like, I don't know what you just said, but I've heard the term spectroscopy before. It's used for, and this is one's interesting to me because I teach engineering. It's used as a model for a bump-shaped disturbance in fluid flow. I'm sure you haven't studied fluid flow, but it turns out like trying to figure out how water flows through pipes is so complicated that people can't really figure it out still. But you can picture, a particle coming along, it's just flowing down a pipe, and then it encounters something, turbulence or maybe a rock on the bottom of the river or a defect in the side of the pipe or something, and it sort of goes around it, if you will, and then takes off again. So I can see that. I can see the logic of that, even though I don't understand the details of this. If you've taken statistics, you might look at that curve and say, hey, that looks like a bell-shaped curve. And that's kind of what it comes down to. Like, this is another actual shape that's similar to a bell-shaped curve and actually does a better job of modeling some things that exist in the world than the classic bell-shaped curve that you may have studied in statistics. And that's pointed out down here. So anyway, it's an interesting curve. But you may also notice one of the things that's kind of cool about it is, notice I set up here, can you see how this curve can be drawn geometrically? In other words, we're just going to graph it and say, oh, look, I got the equation, I graphed it. But notice how it's drawn. If you draw a circle first, you have a XY plane, here's the X and there's the Y, and then you draw a circle right on it there. Okay, great. Well, so we'll say it's a radius, we'll say its diameter is 10, and so this is 10. Do you see how the curve is made? Like you take off, let's look at this one right here. You just take off from the 0, 0 point, any direction you want, and you just take off and fly out into space. And so wherever you hit the circle, you say, hey, look, I just hit the circle. What do you do then? Well, you draw a horizontal line out there, and then you keep going with this line until it hits that horizontal line at 10, and you draw a line down, and where those run into each other, that's a point on the graph. You see how you could draw that geometrically? Like, that's pretty cool that it was, if you will, discovered as a curve just geometrically. Maybe it was just fun. Like, hey, look, I drew these lines through circles and it made this really cool curve. Isn't that beautiful? Yes. Is that enough? Yes, for true mathematicians. But this particular one turned out to model actually, how fluids flow and spectroscopy. It actually modeled some real things in the real world, which is why she's famous and why you've heard of her. If it was just a beautiful curve, she'd just be one of the many nerds who thought a curve was beautiful and no one cared because it didn't model anything. Now, the reason I bring it up is because, well, this is an equation that you know some stuff about, like thanks to what we just did yesterday. So let's go graph one of these things and let's give her the credit she is due for being a stud, a girl stud. Girls be studs.
Spectroscopy is really neat.
Tell us what you know while I'm graphing this.
Took a couple of astronomy classes, and it's basically the ability to tell what an object or a star is consistent of at a long distance by looking at its spectrum that it emits and whatever lines that are missing in the spectrum or something to that nature.
Yeah, now that you say that, I've heard that a little bit, but it has to do with, I've heard of red and blue shift, and based on the wavelength of light, you can actually tell if a star is going away or coming toward you.
Yeah, that's kind of similar, but this is more like not looking at the red and blue shift of the light to tell where it is. It's looking at the actual light that's emanated from the star to tell the composition of it. Because every element and composition, when you look at its spectrum, either has like some gaps in it, or it's, it has little gaps in it that you tell, those are the spectral lines, and that tells you, okay, this is hydrogen or this is helium,
Yeah. That's ringing a bell. Yeah. So you've all heard of the, the spectrum of visible light. And so the word spectroscopy is coming from the fact that light breaks into a spectrum. You've all seen it pass through a prism in a light that's in a chandelier or something like that. Love it. Thanks for bringing that up, Justin.
Yeah, I vividly remember my 9th or 10th grade science teacher brought these little spectrum glasses to class, and he was like, he gave them to everybody, and we actually got to keep them, and he was like, look at these different things and look at how there's breaks in the spectrum. Yeah. And I'll never forget that.
I should say the same thing, but I've seen that too, and I did forget it. So first of all, I took the equation away, but remember how it was y equals a cubed over a squared plus x squared. So I picked it to be 10, and notice, sure enough, you can sort of see the circle there. sitting there at 10, and maybe from your algebra knowledge, you could even write the equation of that circle in there. You should know this from a previous class, but I can actually graph that circle by saying,
I think you might want to switch your screens to your pad. We're still looking at that.
You don't see it. You do know the equation because you're still staring at it. Okay. Okay, so there is Maria Agnesi's graph, and notice it's working. Sure enough, you know, it was supposed to, if you picked a diameter circle of 10, this thing was this spectral line, or this deformation in flow was going to go up to a height of 10 and then get back to level again. And again, I'm probably oversimplifying this because I don't deeply understand it, but I'm thinking of it as just a particle that's like ripping along the x-axis, and then it encounters an obstacle that 0, 0, and it goes up around it, and then it gets back where it was before. And so, you know, maybe that's what she's talking about. But again, this is just an interesting curve. That's what it comes down to. It's a curve that you and I would say we've never seen before. But what I'd like you to do with it now is, well, take its derivative. If it's y equals 1,000 over 100 plus x squared, take its derivative. Can you do that? Should be able to from yesterday. Am I breaking up sound-wise? Because you guys are freezing every now and again.
Yeah, you're breaking up a little bit.
Okay. So can you take the derivative of this equation? I'm going to copy this and bring it into my notes so we can write on it a little bit. You know, and again, in this case, we're just saying slope, but remember, slope means rate of change. In other words, and this is in a sense speed. And so if this is a particle flying along and it has to go around something, it has to go around an obstacle and keep on going, we'd be talking about rate of change would be its speed. So in this case, if we're finding slope, it might be able to say, well, how does the speed of that water particle behave? I mean, it was moving down the pipe at, you know, 15 feet a second, but now it has to go around this obstacle. And so does that cause it to slow down or speed up? And being able to answer the question, what's its speed there, based on, thanks to Maria Agnesi actually having a real equation that models this, we could actually figure out what its speed was. I mean, that's what slope is really doing. And this is a problem from yesterday in the sense that, well, it's a division problem, so this is a quotient rule problem. So stupid, why can't I take a picture? Because I'm stupid, that's why. So we are told the equation is, just to write it a little more normally instead of 10 cubed. First of all, this is maybe surprising to you, but you can't just move the x to the top. Do you understand why not? I wouldn't say that's obvious. But the fact that it's being added to something, you can't just take it away. The opposite of add is subtract. You can't just move that away. If that had been 100 times x squared, then that could have moved to the top, in which case it would have been just a power rule problem. But this is not a power rule problem. You can't do that. You can't divide 1,000 by 100 and say it's 10 over x squared. Like, these are mistakes you should not be making, but you might be. You really don't have a choice here to take the derivative, except but to say, I know how to take the derivative of a fraction. There's an x squared down there on the bottom, and so this is a quotient rule problem. So if we want to find y prime, we're going to need the quotient rule from yesterday. So this is just a quick application / review of the quotient rule. So let's see what the quotient rule say. I'm reminding myself. It was u prime times v minus u times v prime all over v squared. I think that was it. Because it is a little bit memorizable, I got it memorized. So great. What's our derivative then? So this entire mess is our v, that is our u. So what's u prime? What's the derivative of 1,000?
So Doug, would it be easier if we kept her original formula like a cubed over a squared plus x squared?
No, because this is only true for a specific value. In other words, you got to think of, even if you did it originally, you still have to understand a is a constant. In other words, the derivative of a cubed is not 3a squared because a is a constant. And this graph is going to look different. It's going to have a different slope if I choose a different value for a. And so even if you did leave it the same, you have to realize a is a constant. So it's probably easier to pick one like I did as 10. It's a good question. You're all fumbling. What's the derivative of 1,000?
Is it 0?
Yeah, and I like your tone of voice. Like you think it's 0, but you're not sure. Yeah, remember y equals 1,000. If you just left it alone, what's the derivative of 1,000? That's a horizontal line, and the slope of a horizontal line is nothing. The derivative of a constant is 0. So I have 0 times, well, I start writing v down, but I think to myself, why am I even writing this down? Because I'm multiplying it by 0. And then minus u left alone, which is 1,000, but times the derivative of v. What's the derivative of 100 plus x squared?
Zero plus 2x.
Nice. The derivative, we love plus signs, right? We love plus signs. We don't like multiplication and division signs, but we love plus signs. Derivative of 100, just like all constants, is 0. The derivative of x squared is 2x. All over what?
$100 plus x squared squared.
Yeah, and don't do this. Don't say, oh, it's 100 squared plus x squared squared. That's not squaring the bottom. You're screwing up the distributive law. What Connor said was right. It's 100 plus x squared times another 100 plus x squared, which is distributive law. Do you see what I'm saying? And so we, out of efficiency, I won't say laziness, write it like that. And so let's see. So all of this goes to 0. And then I have 1,000 times 0, which is still 0. And then I have negative 1,000 times 2x. So wouldn't that be negative 2,000x on top? And then I have 100 plus x squared squared. Do you think I should distribute the bottom out? Would that be a good idea? And the reason I say that is because I want to know some things. Like I'm curious about, like, what's the slope right here at 3? Like that's what I want to, remember, you don't take derivatives just to take derivatives. You only do that if you're like a math nerd because you think it's cool, and it is cool. But most people are doing it because they want to know, well, what's the speed of that particle right there? I want to know the slope because slope is not just slope, it's rate of change. I want to know what's the speed of the particle. So the whole reason we did this is because we want to know sort of now what's y prime of say 3. Well, you're going to have to put 3 into this. And for that reason, I think it'd be a waste of time to square the bottom out because it's going to get really huge. I'm going to have to plug 3 in a whole bunch of places. Wouldn't you rather just plug 3 in like it sits? So again, these are things that aren't addressed as a part of homework assignments, but it's like, I'm going to use this equation. As I've been saying, what you have now is really a recipe for y prime of x. We have a recipe for slope. And I'm going to use that recipe when x is 3 to see what the slope is. So I'm just going to plug that in. You should almost be able to do this in your head. The top would be negative 6,000, right? And the bottom would be 109 squared. 3 squared is 9, so it'd be negative 6,000. This is what I'm typing in my calculator. Negative 6,000 divided by 109 squared. And based on the picture, what kind of a number should I get? Notice the graph is to scale, like one box to the left, one box up. Like, to me, that slope right there, these are things that you should be thinking now. That slope looks negative and less than 1 to me. So when I type that in and I get negative 0.505, I think, yeah, that makes sense. But I am rounding it off, negative 0.505. And of course, we could, go on and do this for other points and find the slope everywhere. And then we could kind of own the speed of this particle as it rips around this. And this is, by the way, kind of how air moves around a wing. The air has to go faster over the top of a wing of an airplane, which creates less wind resistance up there because it's going faster, and that's what creates lift, and that's why planes fly. Like, this is not theoretical. This is very practical and very beautiful. And this is kind of like that, except for it's saying fluid flow. And you can tell I kind of understand it, but not really, not deeply. But this is why you want to be able to speak the language of calculus. If you end up doing something, interesting, maybe for a job, then maybe calculus will tell you something that you don't know. So that's kind of cool in the sense that that's a pretty ugly equation. And, many of us would have screwed that up, right? Because that's not, you have to use the quotient rule there. There's not a way around that. And that's a fairly ugly expression, isn't it? Like, that's a lot uglier than it was to start with. Derivatives usually make things look a little bit uglier. But that's an example of the quotient rule in action on something actually real, something practical, a real formula and something you haven't seen before. And again, I found this someplace in life and I said, where does that belong? Where would that be interesting? And I threw it in an algebra class and I said, hey, it'd be great for the quotient rule, because here's an equation where you have to use the quotient rule to take its derivative. Interesting. So just for the fun of it real quick, let's go back here and give Maria a hair more respect and kind of look at, how does this graph look if you choose different values? So see how, in a sense, you might say, hey, that's a minor disturbance. That's like hitting a speck of dust or a tiny pebble, whereas this is a, more major disturbance. And so in a sense, this thing just lifts up off the ground and just gets bigger and bigger and bigger. So if I said, let's let the X max go clear to 100, then of course, this thing's just going to grow and grow and grow. And of course, if I redid this where X was, let's leave it 60. If I redid it where X is 60 and I went back to 3 and I said, what's the slope at 3? Can you tell from this picture that it's going to be a lot flatter up there now than it was before? So that's why, you have to consider what A is. Every time X is 3, the slope is not negative 0.5. In this case, it'll be quite a bit flatter up there.
So at 60, at A is 60, does her circle kind of mechanism still work?
Yep. Can you see the circle of diameter 60 sitting in there? I can almost remember how to do this. I'm going to try it real quick, but I want to say it's R equals. We'll tackle this in Math 253, but I think if I say R equals 30. Sine of theta. Oh, that was close. I almost got it. There's something called a polar equation. That's one way to graph a circle. So that's the circle that it's sort of going over the top of, which is kind of cool. Just because this is neat, and I'm going to do one other thing real quick. Because I don't know if I gave you enough time to stare at that geometric interpretation. So I'd like to show it to you now, like actually write on it so you can see it happening. So we just made the equation, if you will. What would the word be? We made it using algebra, kind of algebraic. And you don't know the history of this, but it turns out that mathematicians nearly killed each other over whether geometry or algebra was better. And it was quite a discovery that they did not enjoy for the most part when they realized algebra and geometry are the same thing. So we just graphed that algebraically, right? And for most of us, it just kind of felt like magic. But here's how Maria created this graph. If you take let's go with green. If you take a random line and you draw it, notice I'm just drawing it randomly, and you notice two things. Hey, where did it hit that horizontal line up there? And where did it hit the circle? Did you have time to see this when I pointed it to you a little bit a second ago? And what do you do with those 2 points? You take off horizontally from here and you take off vertically from there. And wherever those hit, that's one of your points. That's one of the points that makes the shape up. And then you say, that was really fun. Let's do it again. So you go over here and you say, where does that one hit the horizontal? It hits about right there. Where does that one hit the circle? About right there. And so then you go out here horizontally until this one hits it vertically, and you say, there's a point. Like if you keep doing that, that creates the curve in a geometric way. Like there's no equations associated with it. So it creates a beautiful curve. That's a really beautiful, sloping kind of a neat curve. It really is beautiful, I think. But not only that, it even applies to things in models, spectroscopy and flow and so forth. And yet it was able to be defined geometrically by using kind of a cool little trick. And it was amazing to think that somebody came up with a way to define it algebraically, isn't it? I mean, isn't that kind of cool? So this distance right here is the A value, whatever A you stick in there, that's what you get for kind of the height of this curve. Way more beautiful than just marching through algebra classes. Geometric. I guess I'll say build. Anybody do any of the assignment yesterday? Did you feel like you understood how to apply the the quotient and because I think the homework assignment for that was relatively straightforward. How to apply the product and quotient rules to sort of kind of basic problems. That takes practice. Anybody want to ask me anything about that? I don't intend that to be tricky. I'm not going to give you tricky questions about it. Well, let's get a jump then. So we're spending the rest of today and next time on 3.5, which is what is the derivative of a trig function? Like those are cool, right? Trig functions are cool. If I go in here and say y equals the sine of, I can say theta or I can say x. You know from math 112 that that's what a sine wave looks like. By the way, this is the first time it's mattered, but does it make sense it now matters if I'm in degree mode or radian mode? It doesn't matter unless you got trig involved. Can you tell if I'm in the right mode? Is this degree mode or radian mode?
Degree mode.
Notice it starts at 0, 0. And let's see, I'll throw a quick slider on here so that you can watch it slide. A comma. And notice I don't have a way of cheating now. Like I want to say, and this is again an argument for why you why you use function notation. I want to say a f of a, so it'll give me the y coordinate, but I didn't define it correctly. So I have to go back here and say I don't want that to be y equals, I want it to be f of x equals. And so that's why function notation was invented. It was not invented to make your life terrible. It did that too, but it wasn't invented for that reason. So right there at 0, 0, cool. But what does it take to get one period? In other words, I went up to this peak, I go down, and now would you agree I just got back to where I started from? I just made a full lap. How far where am I at right there?
A full lap should be 2 pi.
Yeah, the full lap is 2 pi, 6.28. And so that tells me I must be in radians. Otherwise, that would have made a full lap in 360 degrees. And so up here, that little wrench in the upper right-hand corner, see how there's a choice right there? Where is it? I thought it was right here. Oh yeah, at the bottom. See how it says radians and degrees? If I was in degree mode, then that would not have made it back again until 360 way out there. Notice it's kind of way too flat. So, but again, the point is like, this is an interesting curve too. Wouldn't it be interesting to know what its slope is? So how are we going to find the derivative of sine? Like, what's the slope of that? I don't know about you, but you should be thinking, that's not power rule. There's no exponents. It's not quotient rule. There's no divisions. It's not product rule. Like, uh-oh, we're in a new world here. As I said, what you do in boring old normal calculus is just say, derivatives are cool. Let's take the derivative of everything. Now you have my note sheet. You may already know the answer to this. I wouldn't look at it. I'd rather you kind of just play a little bit. But let's use what we learned in, I think it was 3.2, where we looked at the graphs of things. Let's see if you can figure some of this out yourself. So I'm going to make a picture of this, take it over to our screen, but I want you to think about what you can tell some of the slopes there. So let's bring that guy in. Drop it down a little. Make it a little bigger. So let's talk about slope. You know some slopes. Like, what's the slope of it right there? How come I can't draw on it? No, what's the slope right there?
0.
0. Isn't there a whole bunch of places where the slope is 0? The slope is 0 there. The slope is 0 there. The slope is 0 there. There's a whole bunch of places where the slope is 0. So let's think about what the graph of f prime of x would look like. Remember how the graphs were related? We're going to use this to make a discovery here. So that means the graph, since the slope there is 0, that means the graph of the f prime graph would actually have to hit 0 here and here. Notice I'm just going straight up and straight down. Every one of those, the graph would have to hit right there. Do you agree with that?
Would that mean it has to be cosine?
Let's keep looking. So you're proposing cosine. Let's take a look. What would you say the slope is? What kind of numbers is the slope from here to here? The whole time the slope is what?
Positive.
The slope is positive. And would you agree it starts out small positive? And would you agree this is the biggest positive it gets right there? It's actually flattish down here. Let me zoom in on that. Isn't the slope kind of flattish down here and then it gets steeper and steeper? What would you say the slope looks like right there?
1.
Would you agree the slope looks like about 1 right there? So that would mean our derivative graph would kind of hit here. So doesn't it make sense then that it has to be positive? So it's positive. So basically what the red graph is saying is the slope was 0. Now it's 0.2. Now it's 0.5. Now it's 1. And then it starts to drop back down again on its way back to 0. What would you say the slope is over here? All of those. What are those?
Negative.
Those are all negative slopes. And in the same way, so every place between those two, the slope is negative, but in the same way, would you agree here the slope is flat negative, but right here it's probably its steepest? What does the slope look like right there at its steepest negative, would you say?
-1.
Would you agree that it kind of looks like it's aiming at -1? I mean, isn't this a slope of -1 right there? Up 1 over 1? Doesn't that look like about a slope of -1? You agree with that? So that would mean our f prime of x graph would peak at -1 right there. And again, it's going to kind of have that same effect. Do you recognize this graph from Math 112? Justin did. It sure looks as though, my friends, that f prime of x is the cosine of x. In other words, what's the derivative of sine? Notice it's not power rule or quotient rule or any of those. It's like it sort of lives in its own world. In other words, the equation that would tell you is actually the cosine. Now that's rather surprising, isn't it? I mean, isn't that kind of weird? Like, why would it be cosine? That's kind of strange. Let me tell you something from Math 253 that you don't know. But also you've just never stopped to think about this. I don't have this memorized. I gotta look at my notes. I can't remember what this is. From Math 253, I hope you can stay with me through spring term because this is really a cool subject. It turns out that there's a way to rewrite sine, and you can rewrite it like this. It's x and then minus x cubed, and then plus x to the 5th, and then minus x to the 7th, and so on and so forth. And then the x cubed is over 3, and the x to the 5th is over 5, and the x to the 7th is over 7. So you can see the pattern to it. And then there's one more thing about this that you probably don't recognize. Does anybody know what that symbol means in math? Somebody probably do.
Factorial?
Yeah, factorial. So it's an exclamation point. So it doesn't mean like 3, yell it when you say it. No, 3 factorial means 3 times 2 times 1. In other words, it means multiply it all the way down. So 5 factorial is 5 times 4 times 3 times 2 times 1. Comes up in probability. So Math 253 talks about the fact that you can actually rewrite all equations, exponentials, logarithms, sines, all of them have an expansion. Do you recognize what this is called? What kind of an equation is that? And the bottoms are just constants. Just ignore those. If you have something that says x and x cubed and x to the 5th and x to the 7th, what's that called?
Exponential.
No, it's got to be a letter has to be in the exponent for it to be exponential. If they're just numbers up there, in other words, like y equals x cubed plus 3x squared minus 6x plus 2.
Polynomial, right?
Yep, polynomial. It's just got a lot of terms. Do we like polynomials in calculus?
No, I don't.
No, we love them because they're way easier to take derivatives of than anything else because there's no fractions, there's no multiplications. So we don't need the product rule, don't need the quotient rule. We just need the power rule. That's our easiest rule. So yeah, in one sense, no, I don't like them. But in calculus, we like them because they're the easiest function to deal with.
Can I change my mind?
Yes, you can change your mind. Everybody else is going to get polynomials on the next test to take derivatives of, and I'm going to give you natural logarithm because you said that. And it turns out, my friends, that the cosine of x is equal to this expansion, which is kind of like all the even numbers. And there is some beauty here that is breathtaking, and I want to talk about it, but I certainly am not going to because you will die. So just for now, you don't know this, you don't understand where that comes from, but I guess take my word for it. Now, the amazing thing is you and I take this machine for granted, and I'm like the oldest person that use these. Like when I went to school, we were the first group to use these. People before me were like slide rules. But you take it for granted if you bust out your calculator in radian mode, that if you say, I'd like to know what the sine of 6.12549 is, you take for granted that this thing will tell you that. But it's like, how does it know? Remember, sine is the opposite over the hypotenuse in a right triangle. And so how in the world would it know what that is? Like, that doesn't even make sense. It's because some math nerd realized that sine was equal to x minus x cubed over 3 factorial and so forth. Like, that's why you have this machine. If somebody had not invented that, you would not have a calculator that would do it. So you are thankful to calculus. Ultimately, you don't know it, but you're thankful to calculus for creating, for math 253, so that somebody could make a machine that would do things for you that you sort of take for granted. We do this all the time. Don't you take your phone for granted? What's wrong with this thing? Why isn't it connecting? It's like, you don't even understand how it works. But I want you to notice something. What happens if you take the derivative? Let's change colors because this is awesome. What I'm really doing here is showing you sort of why this is true. Like, based on the graph, we're saying, gosh, it looks like the derivative of sine is cosine. But if we went down here and took the derivative of sine, let's just do it up here. What's the derivative of x? This is a power rule problem. You know the answer to this. What's the derivative of x?
1.
It's 1. And then there's a minus sign. What's the derivative of x cubed? Isn't it 3 times x squared? What's the derivative of x to the 5th? Isn't it 5 times x to the 4th? And on the bottom is 5 factorial, which is really 5 times 4 times 3 times 2 times 1. And I'll do one more. Isn't the derivative of x to the 7th 7x to the 6th? And is it 7 factorial? 7 times 6 times 5 times 4 times 3 times 2 times 1. And so on and so forth. What do you notice about that, though?
It doesn't look anything like cosine x.
But you can cancel out the 3 and the 5 and the 7.
Yeah, don't those 3's cancel? Don't those 5's cancel? Don't those 7's cancel? What do you have left?
Cosine x.
Isn't that 2 factorial? And isn't that 4 factorial? And isn't that 6 factorial? Oh my God, it's cosine of x. There's a lot of ways we have access to this, but this is really surprising. I mean, this is unlike any other animal we've ever seen. This is like a duck-billed platypus. What in the world? How do we do this? I gave you one sort of playful way to get at it, and that's kind of why some books include the graph of the original sine and then the graph of its derivative, and how you can kind of see them in each other. You can see how the graphs relate to each other. And in a sense, that would be enough to say, wow, I think the derivative of sine is cosine. But this is more of a technical proof using things you don't know yet. So it's not really fair. But I think it's cool for you to see this. And one of the reasons I'm showing you is because this is a bit of an advertisement as to, like, why would you take Math 253? Most of you don't need it. It's a course I graduated from college without ever taking it because I didn't need it. And then I just taught it last spring for the first time. Never took it, never taught it. And I was like, oh my God, this stuff is so cool. Now I understand where these formulas, these expansions come from and why they work. And it's like, God, math, people are just smart. Man. Who thinks of these things? It's just really cool stuff. So if you like math, if you want to learn more, if your brain's not full at the end of 252, pretty cool class.
I have a question. So how do you find the derivative of cosine?
That's a good question. Let's go investigate cosine now. I paid April to say that, by the way. It's like perfect timing.
Are you
So
sure it
there's the
wasn't?
graph of cosine. So let's do the same thing with it. Let's draw the graph of f prime of x. Let's play with it and see if we can draw the graph of f prime of x. Cosine? So same thing, we're saying, I wonder what f prime of x is equal to. Well, as we did before, the slope there would be 0. So the slope is 0. Here the slope is 0. Here the slope is 0. Here the slope is 0. Notice that cosine and sine are the same graph. I mean, if you were just to look at that without the xy axis, sine and cosine are the same graph. And by the way, one is called sine and one is called cosine. It isn't, again, because they ran out of names. There's a reason for that. So these are both sine waves, if you will. They're sort of generically called sine waves. What's the slope right here? What's the slope through there?
Positive.
It's positive. And again, it maxes at 1. And so right between these two, this thing maxes at 1. So apparently that's the sine wave. And then over here, it's negative. And so the same thing happens, like right in there, it maxes at -1. So apparently that's what f prime of x might look like. So again, it's a sine wave, but like, what is that?
It's negative sine x.
Remember, sine actually looked like this. Sine took off from 0, 0. That's what sine did. So that was the sine of x. And this is kind of like that, except for it's like going the other direction. Do you see what I'm saying? It's like going down here, right? How do you get a graph to do that? Think about a parabola. If a parabola is facing up like this and you want it to go face down, what do? What flips them over?
Negative.
Yeah.
You make a negative.
You multiply it by a negative. And what that's really doing is saying the answer that you got before, you're just going to make it negative, which means it used to be 7. Now it's -7. It flips it upside down. So does it make sense then that it's the sine of x, except for it's just flipped upside down? Now that's not the only way you could name it. But so the answer to April's question is, what's the derivative of cosine? It's negative sine. Now again, look at the note sheet I gave you. That's what it says. Note sheet I give you says the derivative of sine is cosine, the derivative of cosine is negative sine. You're now in a position to understand that. If you have a little time on your hands, you could even go back and take the derivative of this, the derivative of cosine. And apparently what's going to happen is you're going to get this expression, except for all the signs are going to be wrong. You understand that? Like sine, the x was positive, and then this x cubed was negative, and then the x to the fifth was positive. Apparently what you're going to get is this will come out with the wrong sign. It'll be negative, and this will be positive, and this will be negative. Does that make sense? Like that's what apparently should happen. So you can play with that if you want to. So there's 2 key facts that we now know that we didn't know before. If trig, if f of x equals the sine of x, then f prime of x equals the cosine of x. If f of x equals the cosine of x, then f prime of x equals negative sine of x. So that's kind of cool. And it's also kind of weird that the graph itself would be telling you slopes. I mean, that's kind of strange that it would be the case. What's, of course, our next question?
What's the inverse of tangent?
Yeah. What about all the other stuff, right? What are the other trig functions that you learned in Math 112? The first one is tangent, but then there was all the reverses. Can you still remember those?
Secant, cosecant.
Secant and cosecant. And what was the last one?
Cotangent.
Cotangent. So there's actually 6 of them. And you're sort of more familiar and happier and more comfortable with sine, cosine, and tangent because those are the SOHCAHTOA of just normal right triangles. But the last 3, I think of them as just inverses, like the inverse cosine flipped upside down is secant. And I remember this in kind of a dumb way if you don't remember this, but cosine starts with an S, cosine starts with a C, secant starts with an S. Sine starts with an S, cosecant starts with a C. In other words, C's goes with S's. So I remember, I know what sine is, it's opposite over hypotenuse. And then I think, let's see, S goes with C. Okay, cosecant. So cosecant is that upside down. It's hypotenuse over opposite. Like that's how I get it back if I have to have it memorized. But again, I have a note sheet with trig stuff on it in my open math. And in a sense, this might be the first time that you need it. So what we're going to do tomorrow then is take off and figure out what those are. Now, again, you have the right answers on my sheet, and I probably shouldn't have given that to you too soon, but it's like you may remember from Math 112 or trigonometry when you studied it. Hopefully that was just a term or two ago. If it was much further, you're probably like, oh no, I don't remember any of this stuff. But how are we going to find the derivative of tangent and secant? And you may remember tangent's graph has these asymptotes that just take off forever. You probably just barely looked at it, but it just, guys, it's just a crazy graph. We're not going to have the same success. But you may also remember that you can make all the other expressions just from sine and cosine. Like if you know the sine of an angle, if you know the sine of 30 degrees, then you can actually find all the other ones from just that alone. And so they're all made of each other. In other words, all tangent is made of sines and cosines. Cosecant is made of sines and cosines. And so we're actually going to build these 4 from sine and cosine. So in a sense, this is the backbone right here. And then tomorrow we're going to build these ourselves. And you can build them yourself. Like I just need to give you kind of a hint about how you could go about doing it. And you'll be on your way to do that. What I would recommend for those of you for whom this has been a while, again, I'm just going to go back into my open math to show you where this is. I showed it to you yesterday, but if I go into my open math, this is the view you have, and you go into class, you go into course information, basic trig identities. This is my sheet. You may have one you like better. Whoever you took Math 112 probably gave you one of these, and you're probably more familiar with theirs than maybe you are with mine. But I've got sort of 2 pages here of kind of everything you learned in Math 112. We're going to make use of these right here, for instance, tomorrow. And you might think about that between now and then. There's Pythagorean identities we're going to need from time to time. Here's all, and keep in mind, calculus was invented by people that did not have this cool cheat machine that you have. They didn't know what the sine of 31 degrees was, but they only knew what the sine of 30 degrees was because it was one of the examples of ones you could get perfect. And so most calculus books are written where when trig comes up, they only give you these angles. They never say, what's the sine of 35 degrees, or what's the sine of pi over 5 if it's in radians. It's only pi over 6 or pi over 4 or 2 pi over 3. They're always doing that because it allows the answer still to be perfect, and it keeps you from having to bust this out and kind of write rounded off answers. And so you want to be able to read this. In other words, for me, I say, what's the sine of 5 pi over 6? I don't know the answer to that question. So I look at this and I say, there's 5 pi over 6. Sine is which one of those two? It's the X or the Y? Crickets.
The Y.
It's the Y. And you might stay after class and ask me, why is it the Y? You can make that. So it's the Y coordinate. So the sine of 5 pi over 6 is a half. Like you're going to need that as a part of your My Open Math homework. If it says not just, hey, what's the derivative of sine, and you say cosine, but what if it goes on and says, what's the slope of the sine curve at 5 pi over 3. Like you might have to look at this and then you can say, oh, the slope is a half or something like that. Like that's the kinds of questions, because they're not going to say more realistically things like, what's the slope of the sine curve at 31 degrees or at 9 pi over 7 or some weird angle like that. They're going to use these. And they're going to want an exact answer, which will save you time. You don't have to punch calculator buttons, but you've got to see every one of these points as an X and a Y. You've got to know that the X is the cosine of whatever angle you're at, and the Y is the sine. And that of course, over here, the X coordinates are all negative because you're in the second quadrant. The Y coordinates are all positive. If you're down here, they're all negative. If you're in the fourth quadrant, the X's are positive, but now the Y's are negative. So the cosines of all these angles are positive numbers, but the sines, which are Y coordinates, are all negative numbers. And so get this back. Like as I've mentioned before, the hard part of calculus is not calculus. It's the algebra that you got to carry out. And so, when that comes up, are you just going to be lost because you don't know 112 anymore? As I said, it's no shame on you if you don't. You probably don't remember this very well, but do what you can to get it back. And as I've always said, don't hesitate to ask me those questions during class. Don't hesitate to say something like, I don't get why the sine is Y or something like that. And if I feel like that's too long of an answer, I'll say, that's a great question. Let's talk about it after class. If I think, I can answer that right now in like 1 minute, then I'll answer it right then. Don't feel like you can't ask algebra questions. We won't make a ton of use of some of these crazy identities down here, but it'd be good for you to stare at them again, because we are going to make use of them from now. Occasionally something will come up where we need them. And then there's some stuff, law of sines, law of cosines, and I gave you a picture over here. Let's see what else is in here. I don't think you need most of the rest of this stuff. You might need the quadratic formula.
You need that stuff for physics.
Yeah, these are all really cool things here. But graphs of sine and cosine waves, amplitude, period, phase shift, vertical shift, quadratic formula, hint, hint, you need that for your project that you're working on that you owe me on Monday. If you're not using the quadratic formula, you haven't got as deep as you should get in that problem yet. But anyway, there's some cheat sheet stuff there. If you can, I would recommend you print it just so you have it right in front of you and it's real easy for you to find. But do what you can to get that stuff back before tomorrow.
Yeah, I will say I was working on my physics class with somebody who's a friend that we work together. We've been going to school the past year. But it's been a while since he's taken trig, and like one of the 211 questions at the end of the homework was about some hikers that went, this direction this way, then this direction this way, and there was two groups. They both started at the same origin point, and then were they within a distance enough from each other to be able to communicate over walkie-talkies that had 5 kilometers range. Mm-hmm. And he totally didn't remember the law of sines. And I was looking at it and I just saw all these triangles that were right angles. I'm like, I can totally use a lot of sines to figure out all this stuff. Mm-hmm. But so that helped him out quite a bit, because he didn't remember it right off the top of my head. And I was like, well, so I just took, and I was like, oh, that's a trig question.
Yeah. And that's the hardest part about it. And that's what makes math beautiful ultimately, is just being able to say, oh, trig will help me here, or oh, a derivative will help me here, because that's what derivatives do, is they tell us speed. And it's pretty darn hard to speak the language of math. There's a lot to learn in a language that deep. So anyway, I'm going long. Stay after if anything is bugging you. Otherwise, I will see you tomorrow and figure out all the other cool trig function derivatives.
Yeah, I think I'm good, but I did want to tell you that I do appreciate your style of teaching, and I appreciate how you explain things, and I really appreciate how you show us something and you're not like, this is just how it works. You're like, this is why it works, and let's build this. That really helps me understand things more, because I can see something and it's like, oh yeah, it works like that, but why? I always wonder, like, why? And when you show us how to build it, it's like, yeah, that makes total sense. And I just wanted to thank you. I appreciate that a lot.
I appreciate you saying that. I agree. I think understanding why is what makes it both fun and not magic. And it's actually amazing how many of the times that somebody teaches you something in math, you think, wow, some genius. But a lot of times it isn't. Like, it's actually, that's something that's within my ability too. to figure out. But unfortunately, in a math class, what usually happens is the teacher introduces a question, and then the question is answered 10 minutes later. And so
Right.
it kind of takes the real fun out of it, because most of the time in life, you just never thought about it before. I've never thought about it. And then somebody points something out and it's like, wow, that's really interesting. Well, if I had time and if I had knowledge enough, it'd be fun to have like 3 days to go try to figure it out myself before somebody told me the answer. But obviously in a classroom setting, how much calculus would we get through if we did it that way? And so I don't know. I always struggle as a teacher because it's like takes all the fun out of it.
Right.
If you don't talk about.
I've always wondered, like how people figured out these things and how the math worked. But it's like, and that's why as I'm getting further along in my math knowledge, it's like, oh, that's cool. That's how that works. And that's how that works that I was wondering about before, because I'd always look at things in the world and I'm like, oh man, this is just like crazy complex things that I'll never understand, and it's like, well, it's actually, it's complex, but as long as you follow, a set of rules and things that people figured out, it's really not complex. So
yeah. I appreciate you saying that. Thank you, Justin. I really do.
Yeah. Thank you, Doug. You have a good day.
You too. Bye-bye.